Good morning students, welcome to YouTube channel Next is You. So in the last class we studied about the Laplace equation and Poisson equation, also their general solutions. Now in this video we will study about boundary value problem. So boundary value problem is the determination of electric potential in the region when the value of potential or its normal derivative, that is electric field, are prescribed on the boundaries. So it means that we have a potential and its normal derivative on the boundary region. The basic idea is we have a Laplace equation, that is del square V is equal to 0, and Poisson equation, that is del square V is equal to minus rho epsilon naught. Now we need a boundary information so that we can calculate the unique solution of Laplace as well as Poisson equation. Here we have a surface. Now this blue line indicates the boundary of this surface. As we have a region del square V is equal to 0 where the charge density is 0, and with the help of this boundary condition we can calculate the unique solution of this Laplace equation. We can take example of parallel plate configuration. Here we have a plate with potential at V naught and this plate having a potential equal to 0. So this plate is at a higher potential and this plate at a lower potential. Here x is equal to 0. So at x is equal to 0 we have potential value V naught, and at x is equal to d we have a potential value V is equal to 0, and so d is the separation of distance between two plates. Now these arrows, downward arrows, indicate that the electric field is from higher potential to lower potential. Now these type of boundary condition is considered as Dirichlet type, where V is equal to V naught at x is equal to 0 and V is equal to 0 at x is equal to d at a lower plate. Now with the use of these boundary condition we can calculate the solution of Laplace equation. Now we have a solution. Laplace equation become d square V upon dx square is equal to 0 for x direction. Now integrating we have dv by dx is equal to c1, where v is equal to c1x plus c2 after again integrating this equation. Now applying boundary condition that at x is equal to 0 v is equal to v naught. From here we get c2 is equal to v naught. Now again at x is equal to d we have v is equal to 0. Now putting these values in equation, first we have 0 is equal to c1d plus v naught. Now here we can calculate c1 is equal to minus v naught upon d. Now using the value of c2 and c1 in this equation we get a potential Vx is equal to v naught in 1 minus x upon d. And if we take a normal derivative of this potential then we get v naught upon d. Here this is a constant value directed in negative x direction. If we plot a graph between potential and this x, where we can clearly seen from this equation that if we increases the value of d, the value of potential decreases. So with the increase in value of x means at d we have potential is equal to 0. As we put here x is equal to d, then we get 1 minus 1 is equal to 0, so potential is 0. So there is decrease in potential value linearly, decrease in linearly potential value as the value of x decreases. Now if we plot a graph between electric field and this x, then we get a constant value because here the term v naught upon d is a constant. So we get v naught upon d is constant and it's parallel to x-axis. Here from here we interpret that the potential inside the region is uniquely determined by the value of potential on the boundaries. Now we have types of boundary condition. There are three types of boundary condition. First is Dirichlet boundary condition that we studied in the previous slide. Next is Newman boundary condition, and third is a mixed Robin boundary condition. The first is Dirichlet boundary condition. The value of potential is specified on the boundary, that is V is equal to V1 or V is equal to V2. By using this boundary condition, we can calculate the general solution, specific solution, or we can say that unique solution of the potential of a Laplace equation. In mathematical form, we can represent it the form of V is equal to a given function on surface. Newman boundary condition, where the normal derivative of potential is nothing but a electric field, is specified on the boundaries. So here is the normal potential, and the derivative of V have a specified value G given on the surface. Now since E is equal to minus del V, and this implies that minus curl V upon curl N is equal to E, that is electric field. This is the normal component, E, and N is the normal component. Now the mixed Robin boundary condition, it's also called as the Robin boundary condition. The combination of the potential and its derivative is specified, means it is the combination of Dirichlet boundary condition as well as the Newman boundary condition, and mathematically it's represented as AV plus B curl V upon curl N is equal to C, where A, B, C are given function or constants, maybe a constant. In electrostatic problems, this Dirichlet boundary condition is most common, and we can calculate number of questions in our next lecture with the help of this Dirichlet boundary condition and also with Newman boundary condition. Now we have important theorems and properties. First is uniqueness theorem. If the potential, that is Dirichlet, or its a normal derivative, that is Newman, is specified on the entire boundary of a region, the solution of Laplace or a Poisson equation in that region is unique. Means, for example, if we have this boundary and the Dirichlet condition and the Newman condition is specified in all the these boundaries, then we can say that the solution of Laplace or Poisson equation in that region is unique. Now another is a maximum minimum principle, and it is applicable for Laplace equation. In the charge free region, the potential cannot have a maximum or minimum at any point inside the region. Its maximum and minimum value occur only on the boundary. So if we have this charge free region, there is no charge, here is a charge density is 0. So the maximum value and the minimum value, like we have this parallel plate configuration, no, there is no charge inside these parallel plates. We have only a maximum value and a minimum value corresponding to the boundaries. So this is applicable to only for the Laplace equation. Maximum and minimal principle is applicable for Laplace equation only. Another is mean value property. In mean value property, the potential at any point inside the charge free region is equal to the average of the potential over any spherical surface drawn around that point. Consider this is a point, and in this point we have some potential. If we take a spherical surface around this charge and calculate the average value of potential of that spherical surface, the value of that surface is equal to the value of potential at this point. So this is a mean value property. Now other examples of boundary value problems, we have coaxial cylindrical conductor problem, spherical conductor problem, or rectangular box problem. Here the boundary conditions are specified and R is lies between A and B. We have to calculate here the potential. Also we have to calculate here potential where radius R is greater than capital R. In a spherical conductor we have potential V is equal to V naught, and the other condition is V is equal to 0. So it is at infinity. So with the help of these boundary condition we can calculate the potential value of spherical conductor. Similarly, we have a rectangular box problems, and by using a potential boundary conditions, we can calculate the potential at x, y, z inside the box. So this is all about the boundary value problems. In the next lecture, we will discuss about the various problems that related to net or gate or other physics related exams. We can solve all these problems so that the concept of the boundary value problems clear to you all. Thank you and have a nice day.